Today, we're going to be discussing deep reinforcement learning, which is actually one of a combination of disciplines between deep learning and the long-standing community of reinforcement learning, which has been around for many decades now in machine learning. And at a high level, reinforcement learning provides us with a set of mathematical tools and methods for teaching agents how to actually go from perceiving the world, which is the way we usually talk about deep learning or machine learning problems in the context of computer vision, perception, to actually go beyond this perception to actually acting in the world and figuring out how to optimally act in that world. And I'd like to start by showing a rather short but dramatic video of a trailer of a movie based on the AlphaGo story, which you might have heard of, just to give us an introduction to the power of these techniques.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Lee Sedol.
A match like no other is about to get underway in South Korea.
Lee Sedol is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge.
The whole world is watching.
Can Lee Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think there's something went wrong.
Yeah, it's made a mistake.
He's got to pronounce America.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So for those of you interested, that's actually a movie that came out about a year or two ago, and it's available on Netflix now. It's a rather dramatic depiction of the true story of AlphaGo facing Lee Sedol, but it's an incredibly powerful story at the same time because it really shows the impact that this algorithm had on the world and the press that it received as a result. And hopefully by the end of this lecture, you'll get a sense of the way that this remarkable algorithm of AlphaGo was trained, and kind of going beyond that, Ava will then give a lecture on some of the new frontiers of deep learning as well. So let's start by actually talking about some of the classes of what we've seen in this lecture so far and comparing and seeing how reinforcement learning fits into those classes. So first of all, supervised learning is probably the most common thing that we've been dealing with in this class. We're given data and labels, and we're trying to learn this functional mapping to go from new data to one of the existing labels in our training set. And for an example, we can do things like classification, where I give you an image of an apple, and the algorithm is tasked to determine that this is indeed an apple. Unsupervised learning is what we discussed yesterday, and this deals with the problem where there's only data and no labels. And comparing our problem with the apple example, here I give it another apple, and it's able to learn that this thing is like that other thing, even though if it doesn't know exactly that these are apples, but it's able to understand some underlying structure about these two objects. Now finally, how does reinforcement learning fit into this paradigm? Reinforcement learning deals with something that we call state-action pairs. So this is pairs of both states in the environment that an agent receives, as well as actions that it takes in that environment to execute and observe new states. And the goal of reinforcement learning, as opposed to supervised or unsupervised learning, is to actually maximize the future rewards that it could see in any future time step. So to act optimally in this environment such that it can maximize all future rewards that it sees. And going back to the apple example, if I show it this image of an apple, the agent might now respond in a reinforcement learning setting by saying, I should eat that thing because I've seen in the past that it helps me get nutrition and it helps keep me alive. So again, we don't know what this thing is. It's not a supervised learning problem where we're explicitly telling it that this is an apple with nutritional value, but it's learned over time that it gets reward from eating this and that it should continue eating it in the future. So our focus today in this class will be on reinforcement learning and seeing how we can build algorithms to operate in this state, action, or learning and perception paradigm. So I've defined a couple concepts in that previous slide, like an agent, an environment, action, rewards, that I didn't really define. And I'd like to now start by going through a simple example or a simple schematic where I clearly define all of those things so we can use them later in the lecture and go into greater levels of abstraction. So the idea of reinforcement learning deals with, the central component of reinforcement learning deals with an agent. So an agent, for example, is like a drone that's making a delivery. It could be also Super Mario that's trying to navigate a video game. The algorithm is the agent, and in real life, you are the agent. Okay, so you're trying to build an algorithm or a machine learning model that models that agent, and the agent takes actions in some environment. Now, the environment is, like I said, the place where the agent exists and it operates within. It can send actions to that environment. An action is simply just a possible move that the agent can make in that environment. And here, action is almost self-explanatory, but I should note that the action that the agent executes at time t, here I'm denoting as little a of t, can be chosen from usually a discrete subset of possible actions, which we'll call capital A. So in this first part of the lecture, I'll focus on discrete action spaces, where there's a limited number of possible actions. You can imagine me telling it in a video game, for example, that the agent can go either left or right, forwards or backwards, pick up the block, put down the block. These are all possible actions that you could take in that environment. Now, upon taking an action in the environment, the agent will then receive some observation back from the environment. These observations actually define how the agent interacts with the environment, and it can include things like how the state changes. So an example of a state is, for example, if you're the agent, the state is what you see. So it's the sensor inputs that you obtain. It's your vision, it's your sound, your touch. These are all parts of your state. And basically, it's a concrete situation that the agent finds itself at any given time. So when it takes this action, the environment responds with a new state that the agent is located in given that action. And finally, the last part of this schematic is the reward that the environment responds with given that action. So the reward is basically like a feedback that measures the success or failure of a given action taken in that environment. For example, in a video game, when Mario touches a coin, it gets a reward. From any given state, an agent sends an output in the form of actions to the environment, and the environment returns the agent's new state and an associated reward with that action. Rewards can be either immediate, where you take an action and you immediately get a reward, or they can be delayed in the context of delayed gratification, where you may take an action today that you may not benefit from until tomorrow or the day after tomorrow, or even in some cases, very long term into the future. So, building on this concept of rewards, we can define this notion of a total reward that the agent obtains at any given time, the total future reward rather, as just the sum of all rewards from that time step into the future. So for example, if we're starting at time t, we're looking at the reward that it obtains at time t plus the reward that it obtains at time t plus 1 plus reward at t plus 2, and so on. There's a slight problem here, and that's that if you're going to infinity, if this summation is going to infinity, so if you're looking at infinite time horizons with potentially infinite rewards, this term capital R of t could also go to infinity. And that's not a great property of mathematical equations. So what we do is we introduce this notion of a discounted reward. That's essentially where we discount future actions based on this discounting factor gamma. It's just a number between 0 and 1, where we're placing more weight on rewards obtained in the near-term future and placing less weight on rewards placed in long-term time steps from the current state. So I guess before moving on any further, I want to make sure that everyone understands all of these concepts presented in this schematic, because we're only going to be building on things from this point on and using this terminology to build higher and higher levels of abstraction. So is this all clear to everyone? Yep, go ahead.
So for the state chart change, is that immediately or immediately?
The state change is immediate. So usually you take an action, and that's, let's suppose in like self-driving cars, if you want to train an agent to navigate in a self-driving car world, your action is a steering wheel angle, and the next state is the next camera input that that car sees. It does not need to be related to the reward. So the rewards are basically just a scalar number that come back with each state. But you could also imagine where there are no rewards, and at a given time step, you might not see a reward, but you might see a reward way into the future. So for example, in some games, like, for example, Pong, you can imagine you never get a reward until you either win or lose the game. If you win the game, you get a positive reward, but if you lose the game, you get a negative reward. And all of the intermediate frames and actions that you take never result in any reward at all. So now we're going to take this notion of an agent collecting rewards in an environment and try to define what we call a Q function. This is kind of a fundamental function that's going to be the building block of one of the algorithms that we're going to use in reinforcement learning in the first part of this lecture. And just to reiterate again, this equation which we see on the top is the same equation as before. It's saying the total reward that we can obtain from time t is just the summation of the discounted rewards in the future. Okay, and now we want to define this function, which we're going to call the Q function. And it's going to take as inputs two things. One is the state and the action that the agent wants to execute at that state. And we want that Q function to represent the expected total discounted reward that it could obtain in the future. So now, to give an example of this, let's go back to the self-driving car example. You're placing your self-driving car on a position on the road. That's your state. And you want to know for any given action, what is the total amount of reward, future reward, that that car can achieve by executing that action. Of course, some actions will result in better Q values, higher Q values, because you're going to obtain, if the road is straight, obtaining a higher Q value might occur if you are taking actions corresponding to straight steering wheel angles. But if you try to steer sharp to the right or sharp to the left, your Q value is going to sharply decrease on each end because these are undesirable actions. So in a sense, our Q value, our Q function, is telling us for any given action that the agent can make in a given state, what is the expected reward that it can obtain by executing that action. Okay, so the key part of this problem in reinforcement learning is actually learning this function. This is the hard thing. So we want to learn this Q value function. So given a state and given an input, how can we compute that expected return of reward? But ultimately, what we need to actually act in the environment is a new function that I haven't defined yet, and that's called the policy function. So here we're calling pi of s the policy, and here the policy only takes as input just the state. So it doesn't care about the action that the agent takes. In fact, it wants to output the desired action given any state. So the agent obtains some state, it perceives the world, and ultimately you want your policy to output the optimal action to take given that state. That's ultimately the goal of reinforcement learning. You want to see a state and then know how to act in that state. Now the question I want to pose here is, assuming we can learn this Q function, is there a way that we can now create or infer our policy function? And I hope it's a little obvious here that the strategy we want to take is essentially like we want to try all possible actions that the agent can take in that given state, and just find the maximum, the one that results in the maximum reward. And the one that results in the maximum reward is just going to be the one that has the maximum Q value. So what we're going to define the policy function here as is just the argmax over all possible actions of that Q value function. So what that means, just one more time, is that we're going to plug in all possible actions given the state into the Q value, find the action that results in the highest possible total return in rewards, and that's going to be the action that we take at that given state. In deep reinforcement learning, there are two main ways that we can try to learn policy functions. The first way is actually by, like I was alluding to before, trying to first learn the Q value function. So that's on the left-hand side. So we try and learn this Q function that goes from states and actions, and then use that to infer a deterministic signal of which action to take given the state that we're currently in using this argmax function. And that's like what we just saw. Another alternative approach that we'll discuss later in the class is using what's called as policy learning. And here we don't care about explicitly modeling the Q function, but instead we want to just have our output of our model be the policy that the agent should take. So here the model that we're creating is not taking as input both the state and the action. It's only taking as input the state, and it's predicting a probability distribution, which is pi, over all possible actions. Probability distributions sum up to 1. They have some nice properties. And then what we can do is we can actually just sample an action from that probability distribution in order to act in that state. So like I said, these are two different approaches for reinforcement learning, two main approaches. In the first part of the class, we'll focus on value learning, and then we'll come back to policy learning as a more general framework and more powerful framework. We'll see that actually this is what AlphaGo uses. Policy learning is what AlphaGo uses, and that's kind of what we'll end on and touch on how that works. So before we get there, let's keep going deeper into the Q function. So here's an example game that we'll consider. This is the Atari Breakout game. And the way it works is you're this agent, you're this little paddle on the bottom, and you can either choose to move left or right in the world at any given frame. And there's this ball also in the world that's coming either towards you or away from you. Your job as the agent is to move your paddle left and right to hit that ball and reflect it so that you can try to knock off a lot of these blocks on the top part of the screen. Every time you hit a block on the top part of the screen, you get a reward. If you don't hit a block, you don't get a reward. And if that ball passes your paddle without you hitting it, you lose the game. So your goal is to keep hitting that ball back onto the top of the board and breaking off as many of these colored blocks as possible, each time getting a brand new reward. And the point I want to make here is that understanding Q functions or understanding optimal Q values is actually a really tough problem. And if I show you two possible example states and actions that an agent could take, so for example, here's a paddle with a ball coming straight for the paddle down. The agent can choose to stay where it is and basically just deflect that ball straight back up. That's one possible state-action pair. Another possible state-action pair is where the ball is coming slightly at an angle towards the paddle. The paddle can move slightly to the right, hit that ball at an angle, and just barely nick it and send it ricocheting off into the screen, into the side of the screen, rather. Now, the question I have here is, as a human, which action, state-action pair do you think is more desirable to be in this game? Which of you think it's A? Okay. How about B? Interesting. So actually, you guys are much smarter than I anticipated. Or maybe you're just looking at the notes, because the correct answer is B. Even in a slightly stochastic setting, let's suppose you keep executing A and you keep hitting off these blocks in the middle of the screen. You're kind of having a limited approach because every block that you knock off has to be this one that you explicitly aim towards and hit. So here's an example of a policy executing something like A. And it's hitting a lot of the blocks in the center of the screen, not really hitting things on the side of the screen very often. even though it's not going directly up and down, it is targeting the center more than the side. Okay? Now I want to show you an alternative policy. Now it's B, that's explicitly trying to hit the side of the paddle every time. No matter where the ball is, it's trying to move away from the ball and then come back towards it so it hits the side and just barely hits the ball so that it can send it ricocheting off into the corner of the screen. And what you're going to see is it's going to basically be trying to create these gaps in the corner of the screen, so on both left and right side, so that the ball can get stuck in that gap and then start killing off a whole bunch of different blocks with one single action. So here's an example. It's going to be trying to kill off those side blocks. Now it's going for the left side. And once it breaks open, now you can see it just starts dominating the game because its ball is just getting stuck on that top platform, and it's able to succeed much faster than the first agent in Agent A. So to me, at least, this was not an intuitive action or an intuitive Q value to learn. And for me, I would have assumed that the safest action to take was actually A. But through reinforcement learning, we can learn more optimal actions than what might be immediately apparent to human operators. So now let's bring this back to the context of deep learning and find out how we can use deep learning to actually model Q functions and estimate Q functions using training data. And we can do this in one of two ways. So the primary way, or the primary model that's used, is called a deep Q network. And this is essentially, like I said, a model that's trying to estimate a Q function. So in this first model that I'm showing here, it takes as input a state and a possible action that you could execute at that state. And the output is just the Q value. It's just a scalar output. And the neural network is basically predicting what is the estimated, expected total reward that it can obtain given this state and this action. And then you want to train this network using mean squared error to produce the right answer given a lot of training data. At a high level, that's what's going on. The problem with this approach is that if we want to use our policy now and we want our agent to act in this world, we have to feed through the network a whole bunch of different actions at every time step to find the optimal Q value, right? So we have to, for every possible action, imagine we have a ton of actions. In the previous example, it's simple because we only have left and right as possible actions. But let's suppose we have a ton of different actions. For each action, we have to feed in the state and that action, compute the Q value, do that for all actions. Now we have a whole bunch of Q values. We take the maximum and use that action to act, okay? That's not great because it requires executing this network in a forward pass a total number of times that's equal to the total number of actions that the agent could take at that step. Another alternative is slightly reparameterizing this problem, still learning the Q value, but now we input just the state, and the network intrinsically will compute the Q value for each of the possible actions. And since your action space is fixed in reinforcement learning in a lot of cases, your output of the network is also fixed, which means that at each time you input a state, and the network is basically outputting n numbers, where n is the dimensionality of your action space, where each output corresponds to the Q value of executing that action. Now this is great because it means if we want to take an action, given a state, we simply feed in our state to the network. It gives us back all these Q values. We pick the maximum Q value, and we use the action associated to that maximum Q value. In both of these cases, however, we can actually train using mean squared error. It's a fancy version of mean squared error that I'll just quickly walk through. So the right side is the predicted Q value. That's actually the output of the neural network. Just to reiterate, this takes as input the state and the action, and this is what the network predicts. You then want to minimize the error of that predicted Q value compared to the true or the target Q value, which in this case is on the right-hand side. So the target Q value is what you actually observed when you took that action. So when the agent takes an action, it gets a reward that you can just record. You store it in memory. And you can also record the discounted reward that it receives in every action after that. So that's the target return. That's what you know the agent obtained. That's the reward that they obtained given that action. And you can use that to now have a regression problem over the predicted Q values. And basically, over time, using backpropagation, it's just a normal feed-forward network, we can train this loss function, train this network according to this loss function to make our predicted Q value as close as possible to our desired or target Q values. And just to show you some exciting results, so when this first came out, a paper by DeepMind showed that it could work in the context of Atari games. And they wanted to present this general deep Q network, this learning through deep Q networks, where they input the state of a game on the left-hand side, pass it through a series of convolutional layers followed by nonlinear activation functions like ReLUs, and propagating this information forward at each time using convolutional layer, activation function, fully connected layer activation function, and then finally at the output, we have a list of n Q values where each Q value corresponds to the possible action that it could take. And this is the exact same picture as I gave you before, except now it's just for a specific game in Atari. And one of the remarkable things that they showed was that this is an incredibly flexible algorithm, because without changing anything about this algorithm, but just deploying it in many different types of games, you can get this network to perform above human level on a lot of different tasks in Atari. So Atari is composed of a whole bunch of games, which you can see on the x-axis. So each bar here is a different game in Atari. And things to the left of this vertical bar correspond to situations where the deep Q network was able to outperform the level of a human operator in that game. There are definitely situations in Atari where the deep Q network was not able to outperform human level. And typically what was noticed by a lot of researchers afterwards was that in situations or in games where we don't have a perfectly observable world, where if I give you a state, you can observe you can optimally observe the correct action to take in that state. Not all of these games are having that property, and that's a very nice property to have. So a lot of games have very sparse rewards. For example, this game on the end, Montezuma's Revenge, is notorious for having extremely sparse rewards because it requires that the agent go through a ladder, go to a different room, collect a key, and then use that key to turn a knob or something like that. And without randomly exploring or possibly seeing that sequence of states, the agent would never get exposed to those Q values. It could never learn that this was an optimal action to take. And if it just randomly explores the environment, it's never going to actually see that possible action. And in that case, it's never, ever going to get any context of what the optimal action to take is. In the context of breakout, which I was showing you before, where you have that paddle and the ball hitting the paddle and you're trying to break off all of these points on the top, this is an example of a game where we have perfect information. So if we know the direction of the ball, we know the direction of, or the position of our paddle, and we see all of the points in the space, we can correctly predict with, we have an optimal solution at any given state, given what we see, of where to move the paddle. That kind of summarizes our topic of Q learning. And I want to end on some of the downsides of Q learning. It surpasses human-level performance on a lot of simpler tasks, but it also has trouble dealing with complexity. It also can't handle action spaces which are continuous. So if you think back to the way we define the Q network, the deep Q network, we're outputting a Q value for each possible action it could take. But imagine you're a self-driving car, and the actions that you take are a continuous variable on your steering wheel angle. It's the angle that the wheel should turn. Now you can't use Q learning because it requires an infinite number of outputs. There are tricks that you can get around this with, because you can just discretize your action space into very small bins and try to learn the Q value for each bin. But of course the question is, well, how small do you want to make this? The smaller you make these bins, the harder learning becomes. And just at its core, the vanilla Q learning algorithm that I presented here is not well suited for continuous action spaces. And on another level, they're not flexible to handle stochastic policies because we're basically sampling from this argmax function. We have our Q function, and we just take the argmax to compute the best action that we can execute at any given time. It means that we can't actually learn when our when our policies are stochastically computed. So when the next state is maybe not deterministic, but instead having some random component to it as well. Right, so this is the point I mentioned about the continuous action space being actually a very important problem that might seem kind of trivial to deal with by just binning the outputs, but this is actually a really big problem in practice. And to overcome this, we're going to consider a new class of reinforcement learning models called policy gradient models for training these algorithms. So policy gradients is a slightly different twist on Q-learning, but at the foundation, it's actually very different. So let's recall Q-learning. So the deep Q network takes as input the states and predicts a Q value for each possible action on the right-hand side. Now, in policy gradients, we're going to do something slightly different. We're going to take as input the state, but now we're going to output a probability distribution over all possible actions. Again, we're still considering the case of discrete action spaces, but we'll see how we can easily extend this in ways that we couldn't do with Q-learning to continuous action spaces as well. Let's stick with discrete action spaces for now, just for simplicity. So here, pi of AI for all I is just the probability that you should execute action I given the state that you see as an input. And since this is a probability distribution, it means that all of these outputs have to add up to 1. We can do this using a softmax activation function in deep neural networks. This just enforces that the outputs are summing to 1. And again, just to reiterate, this pi A given S is the probability distribution of taking a given action given the state that we currently see. And this is just fundamentally different than what we were doing before, which was estimating a Q value, which is saying what is the possible reward that I can obtain by executing this action, and then using the maximum, the Q value of maximum reward to execute that action. So now we're directly learning the policy. We're directly saying, what is the correct action that I should take? What is the probability that that action is A1? What is the probability that that action is A2? And just execute the correct action. So in some sense, it's skipping a step from Q-learning. In Q-learning, you learn the Q function, use the Q function to infer your policy. In policy learning, you just learn your policy directly. So how do we train policy gradient learning? Essentially, the way it works is we run a policy for a long time. Before we even start training, we run multiple episodes or multiple rollouts of that policy. A rollout is basically from start to end of a training session. So we can define a rollout as basically from time 0 to time t, where t is the end of some definition of a episode in that game. So in the case of breakout, capital T would be the time at which the ball passes the paddle and you miss it. So this is the time when the episode ends and you miss the ball. Or it's the time at which you kill all of the points on the top and you have no other points to kill, so now the game is over. So you run your policy for a long time, and then you get the reward after running that policy. Now in policy gradients, all you want to do is increase the probability of actions that lead to high rewards and decrease the probability of actions that lead to low rewards. It sounds simple. It is simple. Let's just see how it's done by looking at the gradient, which is where this algorithm gets its name, which is right here. So let's walk through this algorithm in a little more detail. So we do a rollout for an episode given our policy. So policy is defined by the neural network, parameterized by the parameters theta. We sample a bunch of episodes from that policy, and each episode is basically just a collection of state, action, and reward pairs. So we record all of those into memory. And then when we're ready to begin training, all we do is compute this gradient right here. And that gradient is the log likelihood of seeing a particular action given the state multiplied by the expected reward of that action. Sorry, excuse me, that's the expected discounted reward of that action at that time. So let's try and parse what this means, because this is really the entire policy gradient algorithm on this one line. This is the key line here. So let's really try and understand this line. The green part is simply the log likelihood of obtaining or of outputting that action. So let's suppose our action was very desirable. It led to a good reward, okay? And that's just defined by we do our rollout on the top and we won the game at the end. So all of these policies, all of these actions should be enforced or reinforced. And in this case, we did, on the second line, we did another episode which resulted in a loss. All of these policies should be discouraged in the future. So when things result in positive rewards, we multiply, this is going to be a positive number, and we're going to try and increase the log likelihood of seeing those actions again in the future. So we want to tell the network, essentially, to update your parameters such that whatever you did that resulted in a good reward is going to happen again in the future and to even greater probability. So let's make sure that we definitely sample those things again because we got good rewards from them last time. On the converse side, if R is negative or if it's 0, if we didn't get any reward from it, we want to make sure that we update our network now to change the parameters and make sure that we discourage any of the probabilities that we outputted on the previous time. So we want to lower the log likelihood of executing those actions that resulted in negative rewards. So now I'll talk a little bit about the game of Go and how we can use policy gradient learning combined with some fancy tricks that DeepMind implemented in the game of AlphaGo, in the algorithm AlphaGo. And I think at the core, for those of you who aren't familiar with the game of Go, it's an incredibly complex game with a massive state space. There are more states than there are atoms in the universe, and that's in the full version of the game where it's a 19 by 19 game. And the idea of Go is that it's a two-player game, black and white, and the motivation or the goal is that you want to get more board territory than your opponent. The state here is just the board of black and white cells, and the action that you want to execute is just a probability distribution over each possible cell that you need to put your next piece at that cell. So you can train a network, like we were defining before, a policy-based network, which takes as input an image of this board. It's a 19 by 19 image, where each pixel in that image corresponds to a cell in the board. And the output of that network is going to be a probability distribution. Again, it's a 19 by 19 probability distribution, where each cell is now the probability that your next action should be placing a token on that cell on the board. Right, so let's see how, at a high level, the AlphaGo algorithm works. They use a little trick here in the beginning, which is they start by initializing their network by training it on a bunch of experts from, they're training it from a bunch of human experts on playing the game of Go. So they have humans play each other. These are usually professional or very high quality, high level humans. They record all of that training data, and then they use that as input to train a supervised learning problem on that policy network. So this, again, takes as input an action, it takes as input the state of the board, and it tries to maximize the probability of executing the action that the human outputted, executing the action that the human executed. Okay, so now this first step here is focusing on building a model using supervised learning to imitate how the humans played the game of Go. Of course, this is not going to surpass any human level performance because you're purely doing imitation learning. So the next step of this algorithm is then to use that network, which you trained using supervised learning, and to pit it against itself in games of self-play. So you're going to basically make two copies of this network and play one network against itself and use now reinforcement learning to achieve superhuman performance. So now, since it's playing against itself and it's not receiving human input, it's able to discover new possible actions that the human may not have thought of that may result in even higher reward than before. And finally, the third step here is that you want to build another network at each time, at each position on the board. So it takes now the state of the board and tries to learn the value function. And that's essentially very similar to the Q function, except now it's outputting one output, which is just the maximum Q function. So over all actions, this value network is basically telling you how good of a board state is this. So this gives us an intuition. We're using neural networks now to give us an intuition as to what board states are desirable, what board states may result in higher values or more probability of winning. And you might notice that this is very closely related to the Q function. This is telling us, like I said, at the core, how desirable a given board state is. And basically, just by looking at the board state, we want to determine, is this a good board state or a bad board state? And the way that AlphaGo uses this is it then uses this value network to understand which parts of the game it should focus more on. So if it's at a particular state where it knows that this is not a good state to be in, it knows that it shouldn't keep executing trials down the state. So it's able to actually prune itself and have a bit of a more intelligent algorithm of learning by not executing all possible actions at every time step, but by kind of building a smart tree of actions based on this heuristic learned by another network. And the result is AlphaGo, which in 2016 beat Lee Sedol, who is the top human player at Go. And this was the first time that an AI algorithm has beaten top human performers in the game of Go. And this was really a groundbreaking moment. It ties us back to that trailer that we saw at the beginning of class. And finally, just to summarize some really exciting new work from the same team that created AlphaGo, now they've released a new model called AlphaZero, which was published in Science about 1 month ago. And it's a general framework for learning self-play models of board games. So they show it being able to outperform top model-based approaches and top human players in games of chess, shogi, and AlphaGo. So it's actually able to surpass the performance of AlphaGo in just 40 hours. And now this network, AlphaZero, it's called AlphaZero because it requires no prior knowledge of human players. It's learned entirely using reinforcement learning and self-play. And that's kind of the remarkable thing here, is that without using any prior information at all, now we've shown it's possible to, one, learn the likely sets of moves that human players would make. And then the really interesting thing is that it then kind of starts to discard those moves in favor of even better moves that humans never really thought of making. And the really interesting thing is, if you follow this evolution of the rewards going up in time, if you stop it at any intermediate time, especially on the early parts so if you stop in the early training parts, like for example right here, and you look at the behavior of these agents, they behave similar to top human players. So they, especially the actions that they execute in the initial board states, like right when the game starts, they behave very similar to top human players. But then as training continues and the agent starts to discover new and new, more and more different advanced ways of starting the game, it's actually able to create new policies that humans never even considered. And now AlphaZero is being used as almost a learning mechanism for top human performers on these new policies that can improve humans even more. I think this is a really powerful technique because it shows reinforcement learning being used not just to pit humans against machines, but also as a teaching mechanism for humans to discover new ways to execute optimal policies in some of these games. And even going beyond games, the ultimate goal, of course, is to create reinforcement learning agents that can act in the real world, robotic reinforcement learning agents, not just in simulated board games, but in the real world with humans and help us learn in this world as well. So that's all for reinforcement learning. Happy to take any questions, or we'll hand it off to Ava for the new frontiers of deep learning in the next part. Okay, thank you.